I'm not sure why this is not coming up. Oh, here we go. To start with, I have an announcement. Even if you're graduating, you can still do this. There's going to be a summer school class that I'm offering, a new kind of class called Financial Math for Actuarial Science. So even if you're graduating, thought about being an actuary and really want to consider it, you take that class. You probably would want to, sign up for the actuarial exam too on financial math if you're going to put the time and money into it over the summer. Though of course it's not absolutely required. I'm not going to force you to sign up to take the test. This is part of what you could use to help you prep study for the test, as extra motivation. How will I run it? Well, I'm making a bunch of problem-solving videos right at the moment. They're all about 10 minutes long. So far, I've made like 20 of them. And by the end, I might make, 100 to 200 of them, somewhere in there. Those are not required. You don't have to watch those, but they might, my hope is that they'll be helpful. I might also make some lecture videos, but I might also just meet with you personally. If you want to sign up for the class, we can figure out times to meet on a regular basis to help you study for the test. I think in talking, still today is our main focus is going to be the Cauchy-Goursat Theorem. But I think it would be good to take a step back and review what are line integrals all about. First of all, what are scalar line integrals? And it's helpful to think of these in terms of an application. In this case, it would be an application to a mass of a thin wire. These are going to be physics applications. The second kind of integral we're going to review is vector line integrals, what you typically think of when you say a line integral. And the main application there is to work done by a force. We'll review how complex integrals are related to those vector line integrals, talk about Cauchy integral theorem and Cauchy-Goursat theorem, talk about a fundamental class of examples, and if we have time, something called the continuous vector line theorem. All right, so I got a lot of stuff here. And by the way, I did put this on Moodle this morning. You can look under the pre-class notebooks. You'll find lecture 23. You can look at it if you prefer, but I also, you might want to consider writing at least some of this stuff down. I'm going to draw pictures as I talk about it here. Okay, so first of all, what is a scalar line integral? Think of it in terms of application to the mass of a thin wire. So you've got a thin wire in the plane. Call it capital gamma. It doesn't have to be oriented. For vector line integrals and for complex line integrals, the curve, the contour has to be oriented. It's got to have a certain specified orientation specified by an arrow, and that affects your parameterization. We can parameterize this, though when we do pick a parameterization, we have picked an orientation, but again, the orientation doesn't matter. And again, we're going to think intuitively in terms of infinitesimals. We'd like to know the mass of this thing. So imagine cutting out a tiny little piece, an infinitesimal piece of the wire. Again, in the standard real number system, there's no such thing as an infinitesimally small number. But for the sake of pretending and getting some intuition about what's going on, we go ahead and pretend. Okay, that we can zoom in so far, so close that the wire is actually straight. Okay, even though you can't really necessarily do that. How long is this little straight piece? Let's call it ds, an infinitesimal length. S is a common letter used for arc length. ds then is a small arc length, a small distance. Pick a sample point in that tiny little piece. Call it, say, I guess I called it R0. By the way, it's going to be real important here to keep track of what's a vector and what's not a vector. So I tried in typing all this to boldface my vectors. Possible I made a typo somewhere and forgot to boldface one of them. If I see a spot where there's a typo, I'll try to correct it. You've got this function rho that's giving you the density. Rho has a domain that is the contour, or maybe some open set containing the contour. It's got outputs that are non-negative. This is going to be a density, say in grams per centimeter. rho of R0 is going to be the density of the wire at that point, which, since the infinitesimal piece is so small, is effectively the density over the infinitesimal piece we pretend is constant. Then you look at this kind of expression and you think of it as a product. The tiny mass of that tiny little piece of wire, dm, is its density in grams per centimeter, say, times its length in centimeters. This gives you the tiny mass of that tiny little piece. Then the goal is to find the total mass of the entire wire. That's a curve. Because it's curved, you can't just, well, because the density is varying, you have to integrate. You have to add up those tiny little masses. You can think of it conceptually here initially as that kind of thing, thinking of the integral as being a sum, even though it's not really a sum, right? We're doing this pretending. But what is dm? Go ahead and substitute. But you don't have to bother with a subscript of 0 when you write the integral. Just write it as rho of r. That's going to be the total mass. So far, all that is an intuitive idea, essentially, or a conceptual idea about what the mass should be represented by. How do you actually compute it? You've got to use the parametrization. Okay? So here's the way you might consider deriving the ultimate integral that you do. This is the integral that you end up doing in the end. Again, thinking of these infinitesimal quantities or differentials as being things you can manipulate. Think of ds, the tiny little arc length there, as being ds dt dt, as if you could cancel the dt's. We're ultimately going to integrate with respect to time via the parametrization. What is ds dt? It's the rate of change of arc length with respect to time. It's the speed. Also the length of the velocity vector. Here I'm using double absolute value signs like I did in multivariable calculus. For the length of the velocity vector, which is the speed, that expression is what ds dt is. Plug in the parametrization into rho, you get this integral as the thing you actually calculate. All right, well, we will do an example here in a few minutes. But before we do that example, what are some simple situations that we can think about? The simplest situation is if the density is constant. If the density is constant, then you're integrating a constant. You can pull the constant out in front of the integral like that. And do this integral of ds, add up the little arc lengths, that's going to give you the total length. That funny looking thing there is supposed to be a cursive L. That's Mathematica's cursive L. If I write it by hand, I'm going to write it like that. It's a cursive L. Where that's the length of gamma. That integral represents the length of gamma. Okay, so if we happen to know rho is constant, like say 10 grams per centimeter, this is a linear density because you have this thin wire. You could try to eyeball the approximate length of the curve and do that multiplication to get the approximate mass. You could also try to actually find the length of the curve by actually doing this integral, though you'd have to use a parametrization there as well. The average density, if rho is not constant, is defined to be, well, take the mass and divide it by the length. That would give you the average density. And the idea of the average density is helpful for trying to estimate and give meaning to the integral, even if rho is not constant. Let me go ahead and move down here. Well, I guess I shouldn't have erased that, huh? Oh well, it's gone. Right here, if you can somehow get rough estimates of the average density and the length of gamma, you could estimate the integral by just doing this product. I hope that makes some sense. You know, if you replace gamma of r with its average, you could essentially call it rho bar. You could essentially factor that out. You'd have rho bar times the integral of ds. which is the length of gamma. You can just do this product. And this approximation is going to be better and better the smaller gamma is, generally speaking. Use this as an approximate value of the integral to hopefully guess the value of the integral before you actually do it, to give you an idea about whether your answer seems right or not. Okay, here we are to an example. It's the same example as we did before, last week. Except now we're doing it in the real plane instead of the complex plane. T comma t squared for t between 0 and 2. A piece of a parabola. Looks like that. It is oriented based on this particular parameterization, though I could have parameterized it in the other direction if I wanted to, and I get the same mass in the end. That better happen. Here's my density function. You can see it's a function of x and y, so it's defined on the entire plane, though we only care about its values on the curve itself. What we have here then is a visual of the curve along with a contour map of the density function. I could estimate the line integral giving us the mass of the thin wire here, this red curve, by estimating the average density along the curve times the length of the curve. How long is the curve? That's probably easier to try to guess first. Well, it goes from the origin up to the point 24. The distance along a straight line from the origin to 24 would be square root of 20, right? 2 squared plus 4 squared. Square root of 20, which would be between 4 and 5. The curve itself is not straight, so it's a little longer than the square root of 20. You might guess 5, maybe a little bit more than 5. What about the average density? Well, what's the low value of the density? The lowest value is at the origin, which is 1. There's 1.28. Can you see that zoomed in if you need to? 1.28 down there. If you look at the formula for rho at the origin, when x and y are 0, you're going to get 1 gram per centimeter. So the value at the origin is 1. That's the low value. What's the highest value? There it's 20.48. Here it's 21.12. Probably 21. You plug in x equals 2 and y equals 4 into that. You get 4 plus 16 plus 1. You get 21. So is the average density 1 plus 21 over 2? Is it 11? It might be an okay first guess, but it's not going to be exactly 11. Because the level curves for this function are more spread out down here. That means the density is increasing more slowly down here than it is up here where the level curves are closer together. So as you imagine traversing this curve as time goes by, say at a constant speed, which this parameterization doesn't do, most of your time, so to speak, would be in lower density values than in higher density values, because the function is changing more rapidly up here. So the true average density should be less than 11. How much less, that's hard to say. I think I guessed 9. Yep, that's what I did. Here are my guesses. Get rough estimates for these things. Guess an average density of 9 grams per centimeter. Guess a length of 5 and estimate the mass then to be 45 grams. To find the actual mass, we actually have to do the integral using the parameterization. We need the velocity vector so that we can find the speed. Remember, length of the velocity vector. We need to plug the parameterization into rho and simplify. And we need to integrate rho of r of t times the length of the velocity vector, the speed. That's the function to integrate. Ugh, looks kind of nasty. I didn't want to do it by hand. I wouldn't give you one this hard of a test by hand. If I were going to try it by hand, I'd try this trig substitution, though I'm not absolutely positive that it works out nicely, but that would be my guess as far as what to use. Mathematica can do it. There you go. Hey, how about that? It's got an inverse hyperbolic sine function involved, which is really a logarithm, remember. If you tried it by hand, you might write the answer in terms of logarithms. It's related to logarithms. It's doable. And we can do the definite integral too, to get the mass in an exact form in this first spot, and I numerically approximate down there. Hopefully it's not too far from 45, and it's not too far, it's 47. Right? So there's the mass that's in white. So that's a scalar line integral because you're integrating a scalar value function. Rho, the density, is real valued, scalar value. It's a scalar line integral or contour integral over that curve, that contour. All right, let's go on to vector line integrals now. The main application being there, work done by force, which is a little harder to understand than mass of a thin wire. But let's do our best here. So now we need to have an oriented contour. It's got to have a specific orientation. If you use the opposite orientation, you get a different answer. In fact, you get the opposite answer. If the work done by the force along one direction of the contour is 10 joules, would be the same units, then the work done by the force along the opposite direction would be negative 10 joules. You might wonder, how can you have a negative energy? Well, you can with work done. You have negative work. Even though the units are energy, and energy can't be negative. It can happen, that's how you think about it. So gamma is in the plane again, parameterized by this same kind of function, R of t there. No, we're not talking about complex analysis yet. You got a vector field or a force field like this, where D is some domain in the plane, and you know, a domain in general doesn't have to be open and connected, but let me emphasize that this is an open and connected domain, just like we need in complex analysis, that contains gamma. Let me make a drawing again here. I'll make it over here this time. There's gamma. It's got an orientation. It's the path of a particle in some force field, like a gravitational field. You know, masses in gravitational fields are affected by the gravitational field. If it's an electric field, then charges in an electric field are affected by the electric field. And I'm not an expert on this kind of stuff, but you know, I know that basic idea. Charges like protons, electrons. For point particles, though, you know, you can imagine maybe bigger objects that have a certain charge, and think of them like a point particle moving around in some electric field. All right, take an infinitesimal piece. Blow it up so far that you pretend it's straight. But now don't think of that as a length. Think of it as an infinitesimal vector. An infinitesimal displacement. Again, zoom in if it's tough to see here with the camera. Infinitesimal displacement, ds. And you got a sample point again, r0, which, since this is infinitesimal, can be anywhere on that, though I'm drawing it in the middle. Maybe it would make more sense to draw it at the beginning. Not a big deal. This expression right here is supposed to be the tiny work done by the force to move that tiny displacement. Really, F is evaluated at the point here. I didn't bother writing that. This is F of R sub 0. Notice this S here is bold-faced. ds, that's your infinitesimal displacement vector. That's a dot product there. Right there. That's not a multiplication of numbers, that's a dot product of vectors. And as a dot product of vectors, you can use facts you know about dot products. You can rewrite the kind of work done in this way. Well, this is true. And and where theta is the angle between f of ds. Right? Remember dot products? You got this kind of equation. V dot W can be thought of geometrically as the length of V times the length of W times the cosine of the angle between them. That can be derived with the law of cosines from the algebraic definition of the dot product. That's what I'm using here. There's the length of f. This ds that's not bold-faced is the length of that ds with ds bold-faced. And theta is the angle between them. Gamma, this path of the particle, is sitting inside a force field. Okay, what does the force field look like? I don't know. Just, it's a bunch of vectors. It's a vector field. It's a continuous function of this kind of form, the domain being a subset of the plane and the range or the codomain being a subset of the plane, though you think of inputs as being points and outputs as being vectors. At the given point here, let me go ahead and put R0 at the start of the vector. At that given point for this little infinitesimal displacement, the vector field is defined. Now this is an infinitesimal displacement, so the vector field is going to be humongous compared to it. Okay? Way off there, unimaginably longer than ds, okay? I'll draw the finite length. Take the dot product, you're taking the length of f times the cosine of the angle between them. There's the angle between them. That's not infinitesimal. Times this ds, no boldface, that's the length, the infinitesimal length of ds. That would give you the work done by the force to move the object that tiny displacement. To find the total work done, add up those tiny works. I could write a conceptual equation here as well. I could write W is the integral of dW, which is this. It's in joules. So far, it's just a conceptual equation. How you actually compute it, you need to relate it to the parameterization, which I'm not really quite doing yet until the very end down here. What am I doing in between? I'm writing it in different forms. You could think of this vector ds, this tiny displacement vector, as really a velocity vector times the length. This displacement vector ds does have a certain length, ds, no vector symbol. Essentially, this is a scalar multiple of the velocity vector. Why am I using an s there instead of a t? Because this is what's called I'm assuming I've got an arc length parameterization here, unit speed. I'm assuming my velocity vector has a length of 1 right in this. And it would be in the same direction as ds at that moment, right there. That's so that I can replace it with, I can really say it's the unit tangent vector. Arc length parameterization or unit speed parameterization just means the curve is traced out at a unit speed, say 1 centimeter per second or something. On standard units, it would be 1 meter per second. I can then replace that by a unit tangent vector that depends on the arc length parameterization, f dot t. And that's a unit vector, that's the unit tangent vector, its length is 1, so you can write the integral this way. The point of doing that, I'll come to it here in a minute. Okay? There is a good reason to write it this way. Though again, to actually calculate it, you've got to use the actual parameterization that you got, r of t, and the velocity vector, r prime of t. Okay, let's think about a few special cases. First, to get some intuition here. If the force is constant, so the force field is constant, all the arrows are the same length in the same direction. You can pull the force field, a constant force field, out of the integral. You can do this dot product. What is this integral going to represent? It's going to represent the net displacement vector. So again, this is a situation where I'm imagining the force field itself is constant. All the vectors are the same length in the same direction. The curve itself is not necessarily straight. It's got a starting point and an ending point. Delta S is the net change in position, the net displacement vector. Okay. By the way, dot products, remember, are scalars. Work is a number, not a vector. Another simple case is if the force is always perpendicular to the curve, like the unit tangent vector or the velocity vector, or you could say ds. This dot product is always going to be 0. The dot product of two vectors is 0 if and only if either one of the vectors themselves is 0, the 0 vector, or the angle between them is 90 degrees. Cosine 90 degrees is 0. So, you know, the curve could be something wild like this. And the vector field doesn't have to be constant. It doesn't even have to be the constant length. But if it's always perpendicular to the unit tangent vector of the parameterization, or again, the velocity vector, those are all going to be parallel. If it's always perpendicular, these are a bunch of right angles like this, then the net work done, the integral, is going to be 0. Another simple case. Okay, now I'm going to come to a spot where I'm going to make use of this representation. That's a scalar line integral. That ds is not a vector. So we can use our idea about scalar line integrals that we could estimate them by taking the average value of the function times, you know, your rough approximation for the average value times the approximate length of the curve to approximate the integral. First of all, the average value is defined to be this, which equals this. And here we are about the rough approximations. If you can get rough estimates for the average value of this quantity and the length of gamma without integration, then you can estimate the integral, which is the work done by doing a product. The average value of that quantity times the length. This is not a dot product. Maybe I should not put a dot there. Well, okay. That's ordinary multiplication. So let's make use of that with an example now. Same curve as before. T comma t squared. Same interval, 0 to 2. But now I don't have a row, I don't have a density, I've got a vector field. Is this a vector field that would show up as the real and imaginary part of an analytic function? Probably not. I just made this up sort of randomly. It's not likely to be the real and imaginary parts of an analytic function. This is a pure multivariable calculus thing. I can enter these things into Mathematica. And I can make pictures that might be helpful in estimating the integral. So what kind of picture do I have here? So you see a bunch of red arrows. Those red arrows are not the exact vectors in the vector field, but they point in the right directions. It's a direction field. The actual vectors themselves are typically much longer. So these are all scaled down to be the same length. As I animate this, as I let b increase, we're going to see the curve get traced up. Here you see a couple of small vectors, I guess. A black vector and a magenta vector that are going to get longer as I go here. Looks like the black vector is maybe the unit tangent vector or something smaller. I guess it's smaller than the unit tangent vector. Or is it? Well, maybe, okay, I might have. Actually, it is the unit tangent vector, sorry. It's tangent to the curve. The scales, I tried to make the scales in these axes the same, but I don't think I quite succeeded. This is a distance of 5 along this axis. I'm trying to measure here with erasers. Okay, these are two, each eraser is 2 units long on this axis. Is the same true here? Well, maybe it is. Well, not quite. Looks like that's more like 1.75 units long. So the scales are not the same, and because of that, it looks like the black arrow is not quite tangent, but it really is. Modify this to make. I was thinking automatic would make the scales the same, but maybe allow one. Is that better? No, that's worse. Sorry. Thought automatic made the scales the same, but it doesn't seem quite right here. Anyway, it's because the scales are not quite right that the black vector doesn't quite look like it's pointing in the tangent direction. It really is the unit tangent vector, though. What's the magenta vector? The magenta vector is a vector in the vector field at the point that you happen to be at where the black dot is. It's getting longer and longer. The angle's getting bigger and bigger. So, could we estimate the line integral now by estimating the value of the average value of this thing times the length of the curve? Well, we did the length of the curve before. It was about 5. What's the average value of this quantity right there? The length of f times the cosine of the angle. Oh boy, that sounds difficult to estimate. And yeah, it would be difficult to estimate. I guess, you know, what is its value here? It would be the length of this magenta vector times the cosine of this angle. That length, you know, I don't know, about 15, 16. This angle, a bit bigger than 45 degrees. The length of the vector times the cosine of that angle might be in the ballpark of, I don't know, 10 or 11 or something, maybe 12. Here the angle is smaller, so the cosine is bigger, but the vector itself is smaller in length. Looks like it probably goes to 0, though, as you go to the origin. So the average value perhaps should be somewhere between 0 and 11 or 12. Does it spend most of its time, so to speak, in lower values compared to higher values? That's hard to say. As a rough guess of the average value, I'm going to say, what did I say here? I guess 3 there. Why don't I guess 3? I was going to guess higher before looking what I guessed before. I think because, for the most part, the magenta vector is fairly short. I think that's why I did that. I guess a lower than halfway between 0 and 12. Lower than 6. Because it's usually a fairly short vector, even though the angle is usually pretty small. And therefore estimate the integral. Oh, here's a typo. Oh, that's all typo here. I want to estimate the work done. Oh, and I just didn't even change this. 3 times 5, 15 joules. And this is the wrong integral symbol as well. Dangers of copying and pasting. What is the actual integral? It's, not too far from 15. 14.4. In terms of the parameterization, what are we integrating? You're integrating f of rt dot r prime. You could also plot that as a function of t and try to estimate the integral visually that way too. That's an ordinary graph. Estimate the area under the curve. Evidently it's 14.4. Definitely not to scale here. A triangle going like this would have area 1/2 base times height would be about 30. Yeah, our integral is less than half of 30, but close to half of 30. This area is close to half the area under this triangle. Okay? So it gives you the work done by the force, which is related to energy and changes in energy of an object moving around in a force field. Though I don't want to get into that because I'll probably say something wrong. Physicists do use it all the time. All right, let's come back to complex analysis. Again, how are these related to complex integrals? We've seen this before. Given a complex valued function of a complex variable, not necessarily analytic, not analytic necessarily, but you would want it to be continuous typically at least. 3 real imaginary parts u and v, there are 3 important associated vector fields. I'm going to go ahead and use the capital phi notation, which Mathematica makes it look like that. I typically write it like that, though. There's the vector field for the function. I'm using the same notation as I use when I think of the function as a mapping. It makes the sense to call this phi bar because this is kind of like the complex conjugate of that. The v is corresponding to the imaginary part of f. So I've got a negative v there. That's like taking the complex conjugate, so why not use a bar? Here I'm using a star when I switch around the order of u and v. These are 3 associated vector fields for the given complex valued function that are important for integration. Actually, the more important ones are phi bar and phi star. Because we saw this. And that's phi bar, and that's phi star. By the way, the phi bar and phi star, these are just purely my notation, okay? If you're looking at other references, I've never seen any other author use them. My made-up notation. But it makes some sense to me. So I'm going to go ahead and use it. We've seen this before. The complex integral, the complex valued function of a complex variable over some oriented contour is this line integral, vector line integral, plus I times this vector line. And both of these line integrals could be thought of in terms of work done by force fields, this force field and this force field as you travel along that path. Next Monday, we're going to see that this second integral actually can be thought of yet another way as a different kind of integral related to phi bar, but that kind of integral is called a flux integral and gives you flux across a thin membrane, amount of fluid per unit time that's passing through the thin membrane instead of a work done by a force. But I think for today we're going to keep it at ordinary vector line integrals and using these 2 vector fields. Here's an analytic example. I've decided to use f of z equals z cubed. Let's go ahead and enter this code and see if we can use the picture to estimate the integral based on that vector field, those 2 vector fields. So I've got phi here, I've got phi bar here, and I've got phi star here. Okay, partially these vector fields end up being really pretty. That's partially why I enjoy them. So what is this vector field? This is the vector field for phi. In this manipulate, I've got 3 buttons here at the top. One for phi, which is essentially the original function. One for phi bar, which is the conjugate. One for phi star, which is where you switch u and v around. This is the original function. Its vector field, kind of pretty. I've got a contour in it that's the unit circle, oriented counterclockwise. However, even though this vector field is pretty, and even though we could do something fun like calculate the index of the critical point here, the singularity, more importantly for integration are the other two. Phi bar, which looks like this, and phi star, which looks like this. They're also pretty. Could we estimate the integral? This is now phi bar. The ordinary multivariable calculus line integral around this closed contour to this vector field. The brown arrow is a scaled down version of the vector field. It's unit length. So in reality, I should take into account the length of the brown arrow too. Maybe I should put that in there. Let me change this a little bit. Let's see, where would I do the brown arrow here? All this. I guess maybe it's not scaled down actually. That's essentially the vector for the brown arrow. Let's see if it changes length as I move. Changing direction doesn't seem to be changing length. Did I scale it down? It doesn't look like it did. Okay, well, let's not worry about the length. Watch it change direction. It rotates a fair amount. And you might guess, because it's rotating seemingly at a constant rate even, and this animation is slowing down. Very computationally intensive. Because it's rotating around and around and around like this, you might guess then that the integral might be 0. The length might be staying constant, might be varying a little bit, but the angle keeps changing, maybe even in almost like a linear fashion. So the cosine of the angle is changing from positive to negative in a regular fashion as well. The angle between this vector and the unit tangent vector is what I'm talking about. That angle right there. So maybe that means the integral is 0. Similar kind of thing happens with phi star, which is the vector field we integrate for the imaginary part of the complex integral. You go around here, once again, the angle between the vector field and the unit tangent vector for the parametric curve seems to be changing at maybe even a constant rate. We'll get stuck. Very computational. And then because of that, you might guess the answer is 0. And in fact, the answer is 0 by what theorem? As I mentioned before the test. Does the camera person know? Go ahead and say it.
The Cauchy-Goursat.
Cauchy-Goursat, yeah. What did Cauchy-Goursat say? It said, if f of z is analytic on some simply connected domain, the entire plane certainly is simply connected, no holes in it. The integral around any closed contour is going to be 0. F of z here is z cubed, definitely analytic over the whole plane. Here we have a closed contour, the integral is going to be 0. Therefore, the integrals, the real and imaginary parts of the complex integral have to be 0. The ordinary multivariable calculus line integrals have to be 0. Does the integral around the original vector field have to be 0? Not necessarily. It's not important for the complex integral. Will it be 0? I don't know. We're still having rotation here, so it very well may be 0, but I'm not going to even bother trying to calculate it. It's not important. By the way, here's a non-animation showing the relationships between these vector fields. Let's see, the red one is the original UV. UV is in red. Hey, I even have the right colors here. What's in blue? Phi bar, which is U negative V. And the one that's in green is the Phi star, which is VU. So you can get from the red vectors to the blue vectors by reflection across a horizontal line, essentially. Take this red vector reflected across a horizontal line through the middle there, you get the blue vector. And you can get from the blue vector to the green vector by rotating by 90 degrees, because these two vectors are orthogonal. Take that blue vector there, rotate it by 90 degrees with the green vector. They're all, of course, scaled down. Here's a non-analytic example. It's got more than one place where it's 0. And I've plotted those points as well. It's pretty as well. But it is non-analytic. So there's the original vector field for the original function. And those big dots happen to be zeros of the vector field, places where it's 0. You can call those singularities. The corresponding U vector field and the corresponding barred vector field, conjugate, and the corresponding starred vector field are the integrals around this closed contour for these vector fields 0 or not. Again, it's hard to say for sure. I'm going to guess here that they're not. Can I guess positive or negative? That looks difficult to guess as well. Definitely getting positive contributions here, but then all of a sudden it switches to negative contributions here because the angle with the unit tangent vector is now bigger than 90 degrees and the cosine is negative. Then we're getting positive contributions again that look like they're pretty much staying positive. I'm guessing the integral here is positive. So the real part of the complex integral would be positive. What about the imaginary part? Positive contributions continuing to be positive. Now negative contributions. Kind of long. Positive contributions again. Negative. This one's harder to tell, I think. That seems harder to tell. It might be close to 0 for all I can tell. Could we actually do the integral to find out? Let's see. Let's give it a try here. So I'll do it in two parts, a real part and an imaginary part. I'm integrating around the unit circle, so I use the parametrization cosine t, sine t. I'm plugging them into phi bar, and I think I'm going to get a positive number with a positive integral with phi bar. This is an ordinary multivariable calculus line integral. I need to dot that with the velocity vector, which would be negative sine t comma cos t. I'm just differentiating r of t here. This is the real part of the complex integral. This is the one I'm guessing is for sure positive. I hope I'm right. It's positive. What is it approximately? About 7.85. That right there is enough to say the line integral of the original function, f of z, is not 0. which shouldn't be surprising because it's non-analytic. Why is it non-analytic? Because I just made up these functions sort of randomly, and it's not like those are real and imaginary parts of an analytic function if I make those functions somewhat randomly. In fact, I even made them different degrees, second degree and third degree, just to be extra sure that they would not be the real and imaginary parts of an analytic function. What about the other one, the imaginary part of the complex integral? Use phi star. That was one where I thought it was harder to tell if it was definitely positive or not. So this could be positive or negative. Could it be 0? I suppose it's possible, though I don't think it's likely. It is 0. How about that? Okay. I was wrong. But the complex integral's non-zero, because the real part's non-zero. Getting real low on time here. I'm not going to go through the details of what's in here. And it's kind of a slow animation. You can look at it yourself if you like. The book mentions this. It's a fundamental class of examples. CR, maybe I should make it cursive C. CR represents a circle of radius little r centered at the point Z0 here, which is a fixed complex number, oriented counterclockwise, positively oriented. Our textbook does sometimes put the little circle on the integral with an arrow there. Emphasize its closed curve, oriented counterclockwise. The animation is supposed to help you believe what I'm about to write down, though it is very slow in running. N is an integer, right? Z is the set of integers. This gives you 0 if n is not equal to -1, and gives you 2 pi I if n does equal -1. Kind of mysterious. If n does equal -1, the function is really 1 over z minus z0. Integrating that is going to involve a logarithm. If I attempt to use the fundamental theorem of calculus. However, this is not analytic on a simply connected domain, at least if you consider its entire domain. Its entire domain is the entire plane except for z0. Take the point out z0. That's not simply connected. Loops around that point cannot be shrunk to a point without passing through the point that's missing. They don't stay in the domain. And the loop around that point, the inside of it is not a subset of the domain. So it's two different ways of thinking about whether a domain is simply connected. So because of that, it shouldn't be surprising that it shouldn't be necessarily surprising that the integral of that around this loop is non-zero, because the Cauchy-Goursat Theorem does not apply. But the integral can be done, you get 2 pi I, and that's a real fundamental result to know. I do go through the details of the calculation down here. You can look at that. We are about out of time. So I hope that was helpful to review multivariable calculus. I would encourage you to continue reviewing it, and in particular, see if you can find, if you still have your multivariable calculus book, information about the flux integral idea. That's what we'll talk about some next Monday. Then we're going to go on to the next section as well. All right, see you then.